Picture this, a web of dark matter stretching across the universe, its invisible threads holding galaxies in place like a cosmic scaffolding. Now, scientists are discovering that these filaments, vast, diffuse structures composed of the universe's missing mass, might hold the key to a radical idea: dark matter isn't just sitting there silently. It's decaying, and the evidence could be written in the subtle ripples of its decay. If dark matter particles are slowly transforming into gravitons, the hypothetical particles that carry gravity itself, the resulting energy ripples would distort the delicate architecture of these filaments. Imagine peering into the universe's hidden skeleton and seeing cracks forming where dark matter once stood. This isn't just theoretical, it's a new way to hunt for dark matter's secrets, using the very structures it helped build as a cosmic detector. In a groundbreaking development that shifts the way we think about dark matter, scientists have discovered a new method to probe one of the universe's most mysterious properties. By studying the vast, thread-like structures that span the cosmos, known as cosmic filaments, researchers have set new limits on how dark matter might behave. Specifically, they've ruled out certain ways dark matter could decay into hypothetical particles called gravitons, which are thought to carry the force of gravity itself. This discovery, published in Physical Review D, offers a fresh approach to understanding dark matter, a substance that makes up 85% of the universe's mass yet remains invisible to all forms of direct detection. The study, led by David Dunsky of New York University, leverages the intricate architecture of the cosmos to test fundamental questions about the nature of dark matter. Let's explore how this research is reshaping our search for answers in the universe's shadowy depths. Dark matter has been a puzzle for decades. Unlike ordinary matter, which interacts with light and can be seen through telescopes, dark matter only reveals its presence through gravity. Its gravitational pull holds galaxies together and shapes the large-scale structure of the universe, yet it doesn't emit, absorb, or reflect light. This elusiveness has made it incredibly difficult to study. Scientists have long speculated that dark matter might consist of particles that interact very weakly with other matter, but even this remains unproven. Now, a new line of inquiry suggests that dark matter might not be entirely stable. Some theories propose that dark matter particles could decay over time, transforming into other particles or even into gravitons. If this were true, it would have profound implications for our understanding of the universe's evolution and the fundamental forces that govern it. The idea of dark matter decaying into gravitons is still speculative, but it's rooted in the broader field of particle physics. Gravitons, if they exist, are the theoretical carriers of the gravitational force, much like photons carry the electromagnetic force. However, unlike photons, which are well established as real particles, gravitons remain hypothetical. Their existence is a cornerstone of quantum gravity theories, which attempt to unify general relativity with quantum mechanics. If dark matter particles could decay into gravitons, this process would release energy into the cosmos, potentially leaving detectable imprints on large-scale structures. But how could scientists observe such an effect? The answer lies in the cosmic web, the vast network of filaments and voids that make up the universe's large-scale structure. Cosmic filaments are the backbone of this web. These structures, which stretch millions of light-years across, are composed of dark matter and gas, forming a sort of cosmic skeleton. They are the sites where galaxies form and where the universe's matter is concentrated. The distribution of these filaments is not random, it reflects the gravitational pull of dark matter, which has shaped the universe's structure since the Big Bang. By studying the way these filaments are arranged, scientists can infer the properties of dark matter and how it influences the cosmos. But how does this relate to the decay of dark matter into gravitons? The key insight is that if dark matter particles were to decay, they would lose energy, which could alter the way these filaments form and evolve over time. This subtle change might be detectable by analyzing the distribution of matter in the universe today. Dunsky's team built on this idea by using observations of cosmic filaments to set limits on the rate at which dark matter could decay. Their approach hinges on the fact that if dark matter decayed into gravitons, it would release energy into the cosmos. This energy release could affect the structure of the filaments, potentially disrupting their formation or altering their density. By comparing the observed distribution of matter in the universe with theoretical models, the researchers could determine whether such a decay process is possible. If dark matter decayed too rapidly, it would leave behind a different pattern of cosmic structures than what we observe today. By measuring the extent of these structures and their density, the team could infer constraints on the decay rate. This method represents a novel way to probe dark matter without directly detecting its particles, relying instead on the indirect effects of its behavior. The study's findings are significant because they provide a new framework for testing dark matter theories. The researchers analyzed data from surveys that map the distribution of galaxies and dark matter across the universe. These surveys, such as the Sloan Digital Sky Survey and the Dark Energy Survey, have revealed the intricate web of cosmic filaments in exquisite detail. By combining these observations with simulations of how dark matter should behave under different decay scenarios, the team could identify discrepancies that would signal a decay process. Their analysis showed that if dark matter decayed into gravitons at a certain rate, it would produce a different distribution of matter than what is observed. This inconsistency allowed them to set a limit on how quickly dark matter could decay. Specifically, they found that dark matter cannot decay into gravitons at a rate that would significantly alter the structure of the universe within the timeframe we've observed. This conclusion narrows the possibilities for what dark matter could be, offering a new constraint on the theories that attempt to explain its nature. This research is part of a broader effort to understand dark matter through indirect means. Direct detection experiments, such as those using underground detectors to search for dark matter particles interacting with ordinary matter, have so far yielded no conclusive results. Meanwhile, indirect methods, like looking for the byproducts of dark matter interactions or decay, have provided valuable clues. The use of cosmic filaments represents a fresh approach, one that leverages the large-scale structure of the universe as a natural laboratory. By studying how matter is distributed across billions of light-years, scientists can infer the properties of dark matter without needing to observe it directly. This method is particularly powerful because it allows researchers to test dark matter theories on a cosmic scale, where the effects of its behavior could be more pronounced. The implications of this study extend beyond dark matter itself. If dark matter decayed into gravitons, it would have profound consequences for our understanding of gravity and the fundamental forces of the universe. Gravitons, if they exist, are a key component of quantum gravity theories, which seek to reconcile general relativity with quantum mechanics. A decay process involving gravitons would challenge existing models and could lead to new insights into how gravity behaves at the smallest scales. Moreover, the study highlights the importance of considering indirect effects when searching for dark matter. By focusing on the large-scale structure of the universe, researchers can uncover clues that might be missed by more traditional methods. This approach also underscores the value of interdisciplinary collaboration, as it combines insights from cosmology, particle physics, and observational astronomy. While the study provides important constraints on dark matter decay, it does not rule out the possibility that dark matter could still decay in other ways. The researchers emphasize that their findings are a step forward in understanding the behavior of dark matter, not a definitive answer. The decay rate they've ruled out is just one possibility among many, and future studies will need to explore other scenarios. For example, dark matter could decay into other particles, such as neutrinos or photons, or it could interact with itself in ways that haven't been considered. The use of cosmic filaments as a tool for probing dark matter decay opens up new avenues for research, encouraging scientists to think creatively about how to test these theories. In the broader context of dark matter research, this study exemplifies the power of observational cosmology. By studying the universe's large-scale structure, scientists can gain insights into the fundamental forces and particles that shape it. The cosmic web, with its intricate network of filaments and voids, is a testament to the influence of dark matter, yet it also presents a unique opportunity to test its properties. As technology advances and new data becomes available, the ability to analyze these structures will only improve, offering even more precise constraints on dark matter's behavior. This research is part of an ongoing journey to unravel the mysteries of the universe, one that continues to challenge our understanding of the cosmos and the forces that govern it. In conclusion, the discovery that cosmic filaments can be used to set limits on dark matter's decay into gravitons marks a significant milestone in the quest to understand dark matter. By leveraging the universe's own structure as a tool for inquiry, scientists have opened new doors to testing fundamental theories about the nature of the cosmos. While the study does not provide a complete answer, it offers a crucial piece of the puzzle, reminding us that the universe is full of surprises waiting to be uncovered. As research continues, the interplay between observation, theory, and innovation will undoubtedly lead to new breakthroughs, bringing us closer to unlocking the secrets of dark matter and the invisible forces that shape our universe. In the vast, silent expanse of the universe, dark matter has long been a mystery. Comprising an estimated 85% of the total mass in the cosmos, this invisible substance shapes galaxies and clusters through its gravitational pull, yet it remains elusive, interacting only through gravity and leaving no trace of light. For decades, scientists have sought clues about its nature, but the answers have remained just out of reach. Now, a groundbreaking study published in Physical Review D has opened a new avenue in the search for dark matter. Led by David Dunsky of New York University, the research proposes a radical idea: dark matter might not be eternal. Instead, it could decay into gravitons, hypothetical particles that carry the force of gravity itself. But how did scientists arrive at this conclusion? What tools and methods did they use to detect such a subtle, almost imperceptible process? Let's journey through the steps that transformed a theoretical possibility into a scientific breakthrough. The story begins with the cosmic web, a vast, interconnected network of dark matter and ordinary matter that stretches across the universe. This web is composed of immense, thread-like structures called cosmic filaments, which act as highways for galaxies. These filaments are not just passive scaffolding, they are the result of dark matter's gravitational influence, shaping the distribution of visible matter. For years, astronomers have studied these filaments to understand the universe's large-scale structure. But the new research suggests that these structures might hold a hidden message about dark matter's behavior. The key insight came from a simple yet profound question: what if dark matter is unstable? If dark matter particles could decay into gravitons, this process would release energy in the form of gravitational waves. However, such energy would be incredibly faint, making it nearly impossible to detect directly. Instead, the researchers turned their attention to the cosmic filaments themselves. If dark matter decay were occurring, it could subtly alter the distribution of matter in these filaments, creating a measurable effect. The challenge was to find a way to observe this effect across the vast scales of the universe. To tackle this, the team relied on data from some of the most ambitious astronomical surveys ever conducted. The Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DS, have mapped billions of galaxies, providing a detailed 3D map of the universe's structure. By analyzing the distribution of galaxies within these filaments, the researchers could look for anomalies that might hint at dark matter decay. But the data alone wasn't enough. They needed a way to simulate the expected effects of dark matter decay and compare them to real observations. This is where computational models came into play. Using supercomputers, the team created simulations of the universe under different scenarios. In one model, dark matter remained stable, while in another, it decayed into gravitons. By comparing the simulated cosmic filaments to the observed data, they could determine whether the decay hypothesis aligned with reality. The simulations revealed that dark matter decay would cause subtle changes in the density of matter within filaments, creating a ripple effect that could be detected through careful analysis. But how do you measure such a faint signal? The answer lies in the precision of modern observational techniques. The researchers focused on the way light bends around massive objects, a phenomenon known as gravitational lensing. When light from distant galaxies passes through a massive structure like a cosmic filament, it gets distorted, creating a faint glow around the filament. This glow, called the lensing signal, is a direct imprint of the filament's mass distribution. If dark matter decay were occurring, it would alter the mass distribution, changing the lensing signal in a way that could be quantified. To isolate this effect, the team had to account for countless other factors that could influence the lensing signal. They meticulously filtered out noise from foreground and background structures, ensuring that any detected anomaly was truly linked to dark matter decay. This process required advanced statistical methods and machine learning algorithms to distinguish subtle patterns in the data. The result was a highly refined model that could predict the expected changes in the lensing signal if dark matter decay were happening. The next step was to compare their predictions with actual observations. The researchers analyzed data from the SDSS and DES, cross-referencing it with simulations to see if the observed lensing signals matched the decay hypothesis. What they found was both surprising and significant. The observed signals deviated slightly from the predictions of a stable dark matter model. This discrepancy suggested that dark matter decay might be occurring, albeit at a very low rate. However, the team was careful to emphasize that their findings set limits rather than confirming a definitive decay process. The data provided the first concrete constraints on how quickly dark matter could decay into gravitons, narrowing down the possibilities for future experiments. This breakthrough didn't happen in isolation. It was the result of decades of collaboration across disciplines. The study built on decades of research into cosmic structure formation, gravitational lensing, and computational astrophysics. It also relied on the immense datasets collected by ground-based telescopes and space observatories like the Hubble Space Telescope. These instruments, with their unparalleled sensitivity, allowed scientists to peer into the distant universe and map the distribution of matter with unprecedented precision. The integration of these technologies, combined with the power of supercomputing, made the study possible. One of the most impressive aspects of the research was the scale of the data involved. The team analyzed billions of galaxies, each contributing a tiny piece to the puzzle of dark matter's behavior. This required not only powerful computational resources but also innovative data analysis techniques. By leveraging machine learning, they could process vast datasets more efficiently, identifying patterns that would have been impossible to detect with traditional methods. The result was a more accurate and detailed picture of the cosmic filaments, enabling the team to set meaningful limits on dark matter decay. The implications of this study extend far beyond the immediate question of dark matter decay. By demonstrating how cosmic filaments can serve as a probe for dark matter properties, the research opens new avenues for future investigations. It highlights the importance of large-scale structure surveys in uncovering the fundamental nature of the universe. Moreover, it underscores the role of interdisciplinary collaboration, where astrophysics, computational science, and data analysis converge to tackle one of the greatest mysteries of our time. As the research team looks to the future, they are already planning follow-up studies. Upcoming missions like the Euclid Space Telescope and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will provide even more detailed data on cosmic structures. These missions will allow scientists to refine their models, test new hypotheses, and potentially detect subtle effects that could confirm or refute the dark matter decay hypothesis. The journey to understand dark matter is far from over, but each step brings us closer to unraveling the secrets of the universe's invisible scaffolding. In the end, the study exemplifies the power of observation and computation in modern science. By peering into the cosmic web and analyzing its intricate patterns, researchers have taken a significant leap forward in the quest to understand dark matter. The findings remind us that even in the face of the unknown, the universe offers clues if we have the tools, the patience, and the curiosity to seek them out. Composing some 85% of the universe's total mass, dark matter betrays its presence only through gravity, unlike ordinary matter. Yet through new research published in Physical Review D, a team led by David Dunsky of New York University has proposed a new way to hunt for the elusive substance. Their approach involves searching for the decay of dark matter particles into gravitons, hypothetical particles thought to carry the force of gravity itself. This part of our deep dive into cosmic filaments helps set first limits on dark matter's decay into gravitons. Focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, the universe has been a mystery wrapped in shadows. We know dark matter exists because of its gravitational pull, how it bends light, how it holds galaxies together, how it shapes the cosmic web. But what exactly is it? For years, scientists have tried to answer that question, chasing clues through the vast emptiness of space. The journey to understand dark matter began in the 1930s, when Fritz Zwicky first noticed something strange about galaxy clusters. He calculated that the visible matter alone couldn't account for the gravitational forces holding these clusters together. It was a radical idea at the time, but his observations hinted at an unseen mass, dark matter, stitching the cosmos together. Yet, for decades, this idea remained speculative, until the 1970s brought more concrete evidence. Vera Rubin's work on galaxy rotation curves showed that stars in spiral galaxies orbit their centers at speeds that shouldn't be possible if only visible matter existed. The only explanation was an invisible halo of dark matter surrounding each galaxy, its gravity keeping everything from flying apart. These early discoveries laid the foundation, but they also raised a bigger question: if dark matter is so prevalent, why haven't we found it yet? Unlike ordinary matter, which interacts through electromagnetic forces and emits light, dark matter seems to exist in a separate realm, invisible to our instruments. For decades, scientists have tried to detect it directly, searching for rare collisions in underground detectors or looking for faint signals from space. But these efforts have so far yielded nothing. Instead, the focus has shifted to indirect methods, using the gravitational fingerprints of dark matter to map its distribution across the universe. The cosmic web, vast networks of dark matter filaments stretching between galaxies, has become a key target for study. These filaments, invisible to the naked eye, are the scaffolding of the universe, shaping the large-scale structure we see today. But how did we come to understand their existence? The answer lies in the evolution of observational astronomy. In the 1990s, the advent of powerful telescopes and advanced imaging techniques allowed scientists to peer deeper into the cosmos. The Sloan Digital Sky Survey, launched in the early 2000s, mapped millions of galaxies, revealing patterns that could only be explained by dark matter's gravitational influence. By studying how light from distant galaxies is bent by intervening mass, astronomers could infer the distribution of dark matter in the universe. These maps showed something astonishing: dark matter wasn't randomly scattered. Instead, it formed vast, interconnected filaments, like the threads of a cosmic spiderweb. At the intersections of these filaments, galaxies clustered, their gravity bound by the invisible scaffolding. These structures, stretching millions of light-years across, became a focal point for research. But the question remained: how can we use these filaments to learn more about dark matter itself? For years, scientists have speculated that dark matter might not be entirely stable. Some theories suggest it could decay into other particles, or perhaps even into something even more elusive: gravitons. Gravitons, if they exist, are hypothetical particles that carry the force of gravity, much like photons carry the force of light. However, unlike photons, gravitons have never been observed, and their existence remains a cornerstone of theoretical physics. If dark matter decays into gravitons, it would emit a faint ripple in the fabric of spacetime, a gravitational wave. But detecting such a signal would be incredibly challenging, requiring instruments far more sensitive than anything currently available. Enter the new research led by David Dunsky and his team at New York University. Their work builds on decades of effort to understand dark matter's properties, but it takes a novel approach. Instead of searching for direct evidence of dark matter decay, they're turning their attention to the cosmic filaments themselves. These structures, shaped by dark matter's gravitational influence, might hold the key to setting limits on how much dark matter can decay. The idea is simple yet profound: if dark matter particles decay into gravitons, the energy released could disrupt the delicate balance of the cosmic web. The filaments, which are already stretched to their limits by the gravitational pull of dark matter, might show subtle signs of instability if dark matter decay occurs. By analyzing the distribution and structure of these filaments, scientists can infer constraints on the rate at which dark matter might decay. This approach is revolutionary because it shifts the focus from detecting dark matter directly to studying its indirect effects. It's a reminder that sometimes, the answers to the universe's greatest mysteries lie not in what we can see, but in how we can measure what we can't. But how did we get to this point? The journey to understand dark matter's properties has been a long one, shaped by technological advancements and theoretical breakthroughs. In the 1980s, the discovery of the cosmic microwave background, CMB, the faint afterglow of the Big Bang, provided another piece of the puzzle. The CMB's temperature fluctuations, measured by satellites like COBE and later WMAP, revealed the early universe's density variations. These fluctuations matched predictions from models that included dark matter, reinforcing its role in cosmic structure formation. Yet, even as these discoveries accumulated, the fundamental nature of dark matter remained elusive. Theories abounded, from weakly interacting massive particles, WIMPs, to axions, but none had been confirmed. The search for dark matter's identity continued, driven by both curiosity and the need to reconcile observations with the laws of physics. Meanwhile, the study of cosmic filaments took on new significance. These structures, once thought to be mere artifacts of gravitational collapse, are now understood as fundamental to the universe's architecture. They are the remnants of the early universe's density fluctuations, stretched and shaped by the gravitational pull of dark matter. By mapping these filaments, scientists can trace the history of the cosmos, from the first moments after the Big Bang to the present day. But how does this relate to the decay of dark matter? The answer lies in the interplay between dark matter's stability and the cosmic web structure. If dark matter were to decay, it would release energy in the form of gravitons, which could, in theory, alter the distribution of dark matter itself. This energy release might create ripples in the filaments, disrupting their delicate balance. By studying these ripples, scientists could infer the rate at which dark matter might decay. However, detecting such subtle effects requires a level of precision that has only recently become possible. The latest advancements in observational astronomy, combined with sophisticated computational models, have allowed researchers to analyze the cosmic web with unprecedented detail. These tools have revealed that the filaments are not just static structures but dynamic entities, shaped by the ongoing interplay of gravity and dark matter. It's within this context that Dunsky's research emerges. By leveraging the cosmic web structure, the team is exploring a new frontier in dark matter studies. Their work is a testament to the power of indirect methods, where the absence of direct evidence becomes a pathway to discovery. But this approach is not without challenges. The cosmic filaments are incredibly vast, and their structure is influenced by countless factors, from the distribution of ordinary matter to the expansion of the universe itself. Isolating the effects of dark matter decay from these other influences requires meticulous analysis. Yet, the potential rewards are immense. If dark matter does decay into gravitons, the implications would be profound. It would challenge our understanding of fundamental physics, suggesting that dark matter is not as stable as once thought. It would also open new avenues for research, from gravitational wave astronomy to the search for new particles beyond the standard model. The cosmic filaments, once thought to be mere scaffolding, are now becoming a critical tool in the quest to unravel dark matter's secrets. This shift in focus reflects a broader trend in modern astrophysics, the recognition that the universe's most profound mysteries often require looking beyond the obvious. The study of dark matter has always been a puzzle, but with each new discovery, the pieces of the puzzle come into sharper focus. From Zwicky's early observations to the mapping of the cosmic web, the journey has been one of persistence and ingenuity. Now, as researchers like Dunsky push the boundaries of what we know, the next chapter in this story is being written. The cosmic filaments, once a mystery in themselves, are now a key to unlocking the nature of dark matter. And as scientists continue to probe the universe's hidden architecture, they may find that the answers lie not in the dark matter itself, but in the way it shapes the cosmos. What if the very fabric of the universe holds clues to one of the greatest mysteries of modern physics? For decades, scientists have puzzled over the nature of dark matter, a substance that makes up 85% of the cosmos mass yet reveals itself only through its gravitational pull. Unlike ordinary matter, dark matter doesn't interact with light or other forms of electromagnetic radiation, making it invisible to our telescopes. Yet its influence is undeniable. It shapes the structure of galaxies, binds clusters of galaxies together, and governs the universe's large-scale architecture. But what if dark matter isn't as immutable as we think? What if it's not just a static presence but something that could decay over time, shedding energy in ways we've never imagined? This is the question that has recently sparked a new line of inquiry in astrophysics, one that could reshape our understanding of the universe's fundamental forces. At the heart of this exploration lies a surprising connection between the vast cosmic filaments that stretch across the universe and the possibility that dark matter might be decaying into particles known as gravitons, hypothetical carriers of gravity itself. But how did this idea arise, and what does it mean for the future of dark matter research? Let's dive into the unresolved questions, the scientific debates, and the mysteries that still linger in the shadows of the cosmos. The idea that dark matter might decay is not new. For years, physicists have theorized that dark matter could be composed of particles that interact through forces beyond the standard model of particle physics. Some of these theories suggest that dark matter particles might have a finite lifetime, decaying into other particles or even into energy. However, detecting such a decay has proven nearly impossible. Unlike the decay of ordinary matter, which can be observed through the emission of light or other detectable signals, dark matter's decay would leave no direct trace. Instead, scientists have had to rely on indirect methods, looking for subtle anomalies in the way galaxies rotate, the distribution of cosmic microwave background radiation, or the behavior of galaxy clusters. These clues have provided tantalizing hints but have never offered definitive answers. Enter the work of David Dunsky and his team at New York University, whose recent research published in Physical Review D has introduced a novel approach to this age-old mystery. Their work hinges on a seemingly unrelated observation: the structure of the universe itself. Cosmic filaments, those vast, thread-like networks of galaxies and dark matter that span hundreds of millions of light-years, might hold the key to unlocking the secrets of dark matter's potential decay. Cosmic filaments are the cosmic scaffolding of the universe, formed by the gravitational pull of dark matter. These structures are not uniform, they are intricate, web-like formations where galaxies cluster along their length, creating what scientists call the cosmic web. The filaments are thought to have emerged in the early universe as dark matter clumped together under its own gravity, pulling ordinary matter into its gravitational wells. Over billions of years, this process has led to the formation of the galaxies and galaxy clusters we observe today. But how does this relate to dark matter's decay? The answer lies in the way these filaments might respond to changes in the energy density of the universe. If dark matter particles were to decay into other particles, such as gravitons, the energy released could affect the distribution of matter on cosmic scales. Gravitons, if they exist, are hypothetical particles that mediate the force of gravity, much like photons mediate the electromagnetic force. However, unlike photons, which are massless and travel at the speed of light, gravitons are predicted to be massless but interact extremely weakly with other matter. If dark matter decayed into gravitons, the energy released could potentially alter the dynamics of cosmic structures, leaving a detectable imprint on the large-scale distribution of matter. This is where the new research comes in. By studying the structure of cosmic filaments, scientists can look for subtle deviations from the expected patterns of matter distribution. If dark matter were decaying into gravitons, the energy loss could cause slight changes in the way these filaments form and evolve. For example, the decay might lead to a redistribution of energy, potentially affecting the density of matter in certain regions of the universe. By analyzing the statistical properties of cosmic filaments, such as their length, width, and the distribution of galaxies along their length, researchers can search for anomalies that might indicate such a decay process. The idea is that if dark matter were to decay, the resulting energy release could influence the formation of these filaments in ways that are not accounted for by current models of cosmic structure formation. However, the exact nature of this relationship remains speculative. The research team led by Dunsky is not claiming to have detected dark matter decay, but rather to have established new limits on the possibility of such a decay. By comparing observed cosmic filament structures with theoretical predictions, they are able to constrain the rate at which dark matter might decay into gravitons. This is a crucial step, as it provides a framework for future experiments and observations that could either confirm or refute the hypothesis. But even with these promising developments, the question of dark matter's decay remains deeply uncertain. One of the biggest challenges in this field is the lack of direct evidence. Unlike the decay of ordinary matter, which can be observed through the emission of particles or radiation, dark matter's decay would leave no direct signature. Instead, scientists have to rely on indirect methods, which are inherently limited by the complexity of the universe's structure. Cosmic filaments, while promising, are just one piece of the puzzle. Other factors, such as the distribution of dark matter in galaxy clusters, the behavior of gravitational lensing, and the properties of the cosmic microwave background, also play a role in constraining dark matter's behavior. However, each of these methods has its own set of assumptions and uncertainties. For example, gravitational lensing, the bending of light by massive objects, can provide insights into the distribution of dark matter, but it is also influenced by the distribution of ordinary matter and the expansion of the universe. Similarly, the cosmic microwave background offers a snapshot of the early universe, but its interpretation depends on a complex interplay of factors that are still being refined. This means that while cosmic filaments offer a new avenue for investigation, they cannot provide a complete picture on their own. The scientific community is still grappling with how to integrate these various lines of evidence into a coherent framework. The scientific debate surrounding dark matter's decay is as much about the limitations of our current models as it is about the potential for new discoveries. Some physicists argue that the idea of dark matter decay is speculative and that the lack of direct evidence makes it difficult to justify as a serious hypothesis. Others, however, see it as a necessary step in the search for a deeper understanding of the universe's fundamental forces. The challenge lies in balancing the need for theoretical innovation with the rigor of empirical validation. For instance, while the decay of dark matter into gravitons is an intriguing possibility, it raises new questions about the nature of gravity itself. If gravitons are real, they would need to interact with dark matter in ways that are not yet understood. This could have implications for our understanding of how gravity operates on cosmic scales, potentially leading to new theories that go beyond the standard model of particle physics. However, these ideas are still in their infancy, and much work remains to be done to test their validity. The scientific community is therefore divided between those who view dark matter decay as a promising avenue for exploration and those who caution against overinterpretation of the available data. Another layer of complexity arises from the fact that dark matter's properties are still largely unknown. While we know that it interacts via gravity, we have no definitive evidence of its composition. Theories abound, ranging from weakly interacting massive particles, WIMPs, to axions, sterile neutrinos, and even more exotic possibilities. Each of these theories makes different predictions about how dark matter might behave, including whether it could decay or interact with other particles. However, none of these theories have been confirmed by direct detection experiments, which have so far failed to find any evidence of dark matter particles. This means that any hypothesis about dark matter's decay must be considered within the broader context of these unresolved questions. For example, if dark matter is composed of particles that interact via a new force, the decay process could be influenced by the properties of that force. Alternatively, if dark matter is a form of energy rather than a particle, the concept of decay might not apply in the same way. These considerations highlight the need for a multidisciplinary approach to dark matter research, one that integrates insights from astrophysics, particle physics, and cosmology. Despite these challenges, the research on cosmic filaments and dark matter decay represents a significant step forward in our quest to understand the universe. By leveraging the structure of the cosmos itself, scientists are opening new avenues for exploration that could lead to groundbreaking discoveries. However, it is important to recognize that this is just one part of a much larger puzzle. The search for dark matter's properties is a complex and ongoing endeavor, one that requires both theoretical ingenuity and experimental precision. As new data becomes available and our models of the universe continue to evolve, we may one day uncover the true nature of dark matter and perhaps even find evidence of its decay into gravitons. Until then, the mysteries of the cosmos remain as vast and intricate as the filaments that stretch across the universe, waiting to be unraveled by the next generation of scientists and explorers. As we look ahead, the quest to unravel the mysteries of dark matter is entering a new phase, driven by cutting-edge missions and instruments poised to test the boundaries of our current understanding. The study led by David Dunsky and his team has opened a fascinating avenue for exploring dark matter's decay into gravitons, but confirming or refining these ideas will require the next generation of observational tools. These instruments, designed to peer deeper into the cosmos and detect subtle signals, will either validate the hypothesis, challenge its assumptions, or even reveal entirely new phenomena. Let's explore how these future missions and experiments could shape the next chapter in this cosmic mystery. One of the most promising frontiers lies in the realm of large-scale structure mapping. Cosmic filaments, the vast, thread-like networks of dark matter that form the scaffolding of the universe, are central to the new research. To study these structures in greater detail, astronomers are turning to advanced surveys that will map the distribution of matter with unprecedented precision. The James Webb Space Telescope, JWST, for instance, is already revolutionizing our view of the early universe, and its successor missions such as the Nancy Grace Roman Space Telescope will build on this by capturing even more detailed images of galaxy clusters and dark matter distribution. These telescopes will not only refine our knowledge of cosmic filaments but also help identify subtle distortions in light caused by gravitational lensing, which could hint at dark matter's interactions. If dark matter particles decay into gravitons, such distortions might reveal anomalies that align with the new theory, offering indirect evidence. Complementing these space-based observatories are ground-based projects that will expand our ability to map the universe's hidden architecture. The Vera C. Rubin Observatory, set to begin operations in the coming years, will conduct the Legacy Survey of Space and Time, LSST, an ambitious effort to catalog billions of galaxies and track their movements over decades. This survey will provide a dynamic picture of how cosmic filaments evolve, potentially uncovering patterns that could be linked to dark matter decay. Similarly, the Euclid mission, a space telescope developed by the European Space Agency, is designed to map the distribution of dark matter across the universe using weak gravitational lensing. By analyzing how light from distant galaxies is bent by unseen mass, Euclid will create a three-dimensional map of dark matter's distribution. If the decay of dark matter into gravitons alters the structure of these filaments, Euclid's data could reveal deviations from expected patterns, providing critical clues about the process. Beyond mapping the structure of the universe, the search for dark matter's decay also hinges on detecting the hypothetical particles themselves, gravitons. While gravitons remain purely theoretical, their existence could be inferred through indirect means. One such method involves gravitational wave observatories, which have already transformed our understanding of cosmic events like black hole mergers. Instruments like LIGO and Virgo, which detect ripples in spacetime, are now being refined to search for fainter signals that might arise from dark matter decay. If dark matter particles decay into gravitons, the process could generate low-frequency gravitational waves that linger in the universe's cosmic background. Future upgrades to these detectors, such as the Plan LISA Laser Interferometer Space Antenna, a space-based gravitational wave observatory, will be capable of probing these signals with greater sensitivity. LISA, set to launch in the 2030s, will be able to detect gravitational waves from sources that are too distant or too faint for ground-based observatories, potentially uncovering evidence of dark matter's decay. Another avenue for exploration lies in the realm of radio astronomy. The Square Kilometre Array, SKA, a next-generation radio telescope currently under construction, will offer an unprecedented ability to study the distribution of neutral hydrogen in the universe. This gas, which is influenced by dark matter's gravitational pull, could provide indirect insights into the behavior of dark matter. By mapping the 21-centimeter hydrogen line across the cosmos, the SKA will create a detailed map of the large-scale structure of the universe. If dark matter decay into gravitons affects the distribution of this gas, the SKA's observations might reveal subtle changes in the way hydrogen is distributed, offering yet another way to test the hypothesis. Additionally, the SKA's sensitivity could help detect faint signals that might arise from interactions between dark matter and ordinary matter, further expanding our understanding of its properties. While observational missions will play a crucial role, the search for dark matter's decay also requires advancements in particle physics experiments. Underground detectors like Xenon and LUX, which search for dark matter particles by detecting their rare interactions with ordinary matter, may need to be recalibrated to account for the possibility of dark matter decaying into gravitons. If such decay occurs, it could introduce subtle changes in the way dark matter interacts with detector materials, potentially leaving behind detectable signatures. Future experiments, such as the upcoming LZ-Lux-Zeppelin experiment, will operate at even lower thresholds, increasing their chances of capturing any anomalies that might arise from dark matter's decay. These experiments will not only test the new hypothesis but also refine our understanding of dark matter's fundamental nature, whether it decays into gravitons or interacts in entirely different ways. Theoretical models will also evolve as new data emerges, shaping how scientists interpret the results of these missions. The study by Dunsky and his team has already sparked discussions about how dark matter's decay could influence the universe's expansion and structure formation. However, the full implications of this hypothesis remain unclear. For example, if dark matter decays into gravitons, it could affect the rate at which cosmic structures form or alter the distribution of dark matter over time. Future simulations and theoretical frameworks will need to incorporate these possibilities, refining predictions that can be tested against observational data. This interplay between theory and observation will be essential in determining whether the decay hypothesis holds up under scrutiny. Moreover, the search for dark matter's decay is not without challenges. One of the biggest hurdles is distinguishing between the subtle effects of dark matter decay and other phenomena that could produce similar signals. For instance, cosmic filaments themselves are influenced by a complex interplay of gravitational forces, and any deviations from expected patterns could have multiple explanations. Future missions will need to employ sophisticated statistical methods to isolate the effects of dark matter decay from other variables, ensuring that any findings are robust and well supported. This will require collaboration across disciplines, as astronomers, physicists, and data scientists work together to design experiments and analyze results with the highest precision. In addition to confirming or refuting the decay hypothesis, these future missions could uncover entirely new aspects of dark matter's behavior. For example, if dark matter decay into gravitons is not the correct explanation, it could point toward alternative theories, such as modifications to gravity or the existence of other hidden particles. The universe is full of surprises, and the search for dark matter is no exception. By pushing the limits of our observational and experimental capabilities, scientists are not only testing the predictions of the Dunsky study but also opening the door to discoveries that could redefine our understanding of the cosmos. As these missions and experiments unfold, they will serve as a bridge between the theoretical framework proposed by Dunsky's team and the empirical evidence needed to validate or challenge it. The journey ahead is as much about refining our tools as it is about rethinking our assumptions. Whether the results confirm the decay hypothesis, reveal new phenomena, or lead to unexpected breakthroughs, they will undoubtedly shape the next chapter in the story of dark matter. For now, the universe continues to hold its secrets, and the next generation of scientists and engineers is ready to uncover them one observation, one signal, one discovery at a time. Composing some 85% of the universe's total mass, dark matter betrays its presence only through gravity, unlike ordinary matter. Yet through new research published in Physical Review D, a team led by David Dunsky of New York University has proposed a new way to hunt for the elusive substance. Their approach involves searching for the decay of dark matter particles into gravitons, hypothetical particles thought to carry the force of gravity itself. This part of our deep dive into cosmic filaments helps set first limits on dark matter's decay into gravitons. Focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.